All right, we are picking up with part two of the honors final exam review. Now we're going to be looking at waves and sound. The first question asks us what's the relationship between frequency and wavelength. This is again, guys, where the formula sheet is definitely your friend. If you look under sound and waves, the first formula is V equals F lambda. Now you will need to be able to remember that F is frequency and lambda is wavelength. So looking at this equation, if velocity stays the same and frequency goes up, wavelength must go down. So they have an inverse. They're inversely related. Now, if the frequency of a wave is 10 hertz, what is its period? Frequency and period are also inversely related, and it's an even simpler formula. It says that F equals 1 over period, or period equals 1 over frequency. We're going to use the second one because we've been told F is 10. So to get period, we would do 1 over 10, which is 0.1. Period is a measurement of time, so that's 0.1 seconds. Now on the second one, if the frequency of a wave is 10 hertz and the distance between a crest and an adjacent trough is 2 meters, what is the speed of the wave? Now we want to be able to use that formula up there, speed equals frequency times wavelength, but you have to notice that what they've given us isn't actually the wavelength. Wavelength is crest to crest or trough to trough. So by giving us crest to trough, that's half the wavelength. So half the wavelength is 2, the full wavelength is 4. So then we can just say 10 times 4 will give us a speed of 40 meters. All right, we are continuing with waves. Now it wants us to explain the following wave behaviors. So a reflection is the bouncing of a wave at a new medium. Refraction is the bending of a wave entering a new medium. Diffraction is the spreading of a wave through an opening. And interference is the interaction between two or more waves. You can have positive interference where they add together and make a larger wave, and you can have negative interference where they cancel each other out and end up with a smaller wave. All right, define the following wave characteristics. Amplitude is height of wave. This is directly related to energy. Frequency is the time. Wait, no, I got that wrong. Frequency is waves per second. So frequency is how many waves happen per second. Period is what I was trying to say before. Period is the time for one wave. And wavelength is the length of one wave. It's important to note that this is crest to crest or trough to trough, but it is not crest to trough. Problems will try to trick you with that. All right, contrast, electromagnetic, and mechanical waves. Give an example of each. Mechanical waves require a medium. They can be transverse or longitudinal. And a good example is sound. Sound is a longitudinal mechanical wave, and it does require a medium. Electromagnetic waves do not require a medium. They're always transverse. And an example is light. How do longitudinal waves differ from transverse waves? Longitudinal waves, particles move parallel to wave direction. I'm running out of space all over the place. That's longitudinal. Transverse particles move perpendicular. The best way to do those is with a picture, so let's come over here. This is a transverse wave. Look at my beautiful picture. Okay. Transverse, longitudinal. Beautiful. Hopefully that's sort of clear. What does the speed of a particular type of wave depend on? So what this is asking is for light or for sound, what determines how fast it moves? And the answer is the medium. For example, sound travels faster in water than it does in air. Light is the opposite and travels slower in water than it does in air. This I actually answered further up without realizing it was a separate question. Amplitude has to do with wave energy. Number 9 has to do with pendulums, which we didn't learn about, so it won't be on our final, but if you're curious, the only thing that can change the frequency of a pendulum is the length of the swinging bar. But again, did not learn. All right, waves are a method of transferring energy. They do not transfer particles. Describe the principle of superposition. All right, the principle of superposition has to do with interference. It just says if you have two waves in the same place, you can algebraically, whatever, that's so wrong, combine them, which means you can add or subtract them depending on whether they are interfering positively or negatively. Beats, those are another thing we didn't learn about. Woo! You can tell this review is a couple of years old. I will try to update it before next year, but that doesn't help you guys. Alright, define the following terms that are associated with sound. So resonance is what explains how you can break glass with sound. And resonance is when an object is forced to vibrate at its natural frequency. Everything has a natural frequency. A dramatic increase in amplitude occurs. So, when you cause something to vibrate at its natural frequency, like playing a note that's at the natural frequency of a glass, it starts vibrating at that frequency. Because it matches the natural frequency, you get a huge increase in amplitude, which means a huge increase in wave energy, and that's what causes the glass to break. Echoes are a little bit simpler. Echoes are reflections of sound waves. So an echo is just when a sound wave hits a barrier and bounces back. That's a reflection. This next one, what is the condition necessary for the Doppler effect to occur? This is that either the source of the sound or the observer, the person listening to the sound, observer, must be moving. And they can't both be moving at the same speed. They have to be moving with respect to each other. So they have to either be getting closer to each other or getting further apart from each other. Okay, this is an example of a Doppler effect. As an ambulance sounding its siren approaches a listener, the listener encounters the sound waves more frequently, because it's approaching more frequently, which results in a higher pitch. As the ambulance sounding its siren moves away from the listener encounters the sound waves less frequently, which results in a lower pitch. If you want more explanation on Doppler effects, in addition to the notes that are posted in this Waves and Sound unit, there are also some really cool little GIFs and stuff online that show how it works. Okay, so I've scratched these two out because we did not learn about the lowest natural frequency of a vibrating object, which happens to be the fundamental frequency, but we don't care because we didn't learn about it. If you look down at number 4, I've already circled faster, but I'm going to explain why. Sound travels faster in a more elastic medium. Now, this one's kind of tricky because you should remember that sound travels fastest in solids. Fastest in solids, next fastest in liquids, and then actually the slowest in gases. And part of you may be like, well, gases should be more elastic because they're more easy to change. But elastic properties isn't how easy they are to change, it's how readily they snap back to their original position. So solids actually snap back to their original position faster, which is why sound can travel faster through them. Sound also travels faster when the air temperature increases because temperature changes the elasticity of the air. The faster the air is, the hotter the air is, the more elastic it is, the faster sound can travel through it. Now we have find the wavelength of sound with frequency of 365 hertz when it is traveling at a speed of 1,230 meters per second. This sound wave is obviously not traveling through air, since sound traveling through air has an average speed of 343 meters per second. This is a lot bigger than that. So we're just going to use the same formula that we used for generic waves. You're going to have V equals F lambda. We're given V, we're given F, so we're going to say 1230 equals 365 times lambda. Grab my calculator. 1230. We'll divide both sides by 365. And we will find that the wavelength of this wave is going to be 3.37 meters. Alright, we are moving right along to light. And now I'm supposed to define these associated terms. Luminous is anything that creates light or emits is the word that's usually used. Illuminated is anything that reflects light. The classic examples of these are that the sun is luminous. We can see it because it's creating its own light. The moon is illuminated. We can only see it because it's reflecting the sun's light. Opaque is something that does not allow light to pass through. Transparent allows all EM waves of a specific type through. Like glass is transparent to visible light, but it's not transparent to UV or IR. Translucent allows some light through, but not enough to create a clear image. This is like frosted glass or something. All right, the regions of the electromagnetic spectrum from lowest to highest frequency. So lowest frequency is going to be radio, so we'll go from radio up to gamma. I'm sort of tempted to sing the song on this video, but it would sound really bad and I would be embarrassed. So we have radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. Beautiful. I'm not going to spend much time on this. Describe the modern view on light. Light is, in modern physics, light is thought to be both a particle and a wave at the same time, but that's not really something we focused on, so I'm not going to write anything else there. Just know that if you're asked, like, is light purely a particle? Is light purely a wave? The answer to either of those is no. It behaves like a particle sometimes when it interacts with matter, and it behaves like a wave when it's just traveling through space. All right, what are the three primary colors of light addition? This is when you have to remember that your art classes lied to you. The primary colors of light addition are red, blue, and green, green being the weird one. A plane mirror always forms a virtual, upright, same size image. That should make sense to you. When you see yourself in your bathroom mirror, it looks like you are in imaginary space behind the mirror. You are not upside down, and you are the same size as real life. Now, why is the sky blue? Because air particles are good at scattering blue and violet light, which is to say short wavelength light. But we're not good at seeing purple, so we just see blue. Why do rainbows form? Rainbows are light refracting from water particles in the air. That's why you need it to have rained recently and for the sun to be shining, because you need a source of light and you need water particles in the air. You can't even see what I'm writing. Sorry, guys. All right, what are the differences in real and virtual images? Real images are always inverted. And can be projected on a screen because they occur in real space, so they can be projected. Virtual images are always upright, but cannot be projected because they do not occur in real space. They occur in imaginary space that your brain makes up. Whew. The two laws. Okay, before defining the two laws of reflection, I'm going to draw a really basic picture showing reflection and then refer to it. Here is some reflective surface. We have a normal line, which is a line perpendicular to our surface. We have an incident ray over here, which is light coming in. And then we have a reflected ray over here, which is light going out. We also have an incident angle and a reflected angle. So the two laws. The first law says that the incident ray, 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 the incident ray the reflected ray. I can talk so much, I can't talk and write at the same speed, and it's annoying. The reflected ray and the normal lie in the same plane. So basically we're dealing with a two-dimensional image here and not trying to worry about 3 dimensions is what the first law says. And the second law says the angle of incidence which I wrote as theta I is equal to the angle of reflection theta r. So those two angles way back over here in my picture are just equal to each other. Alright, use Snell's law to solve the following problem. Here we're going to be like, Snell's law, okay. Light travels through a material at 2.2 times 10 to the 8th meters per second. So V, usually this is V material. The county formula sheet writes that whole word out, which is awkward. V material equals 2.2 times 10 to the 8th. And then we're looking for the index of refraction, which is N. N equals question mark. We're going to go to our formula sheet. Finds that we have this formula that says that N is equal to C, which is the speed of light in a vacuum, over V material. So that's the formula we're going to use. N equals C over V material. C is 3 times 10 to the 8th, which you don't have to memorize. It's on that formula sheet. So N equals 3 times 10 to the 8th over 2.2 times 10 to the 8th. And we're going to get a value for N of 1.36. N is a ratio, so it does not have units, and it should always be a positive number greater than 1, because if you get a negative number or a number less than 1, that means that light is moving faster in the new material than in vacuum, and that's impossible. We don't want to break the laws of physics. Number 9, what is meant by complementary colors of light? This was on a quiz and a lot of people got it wrong. Complementary colors of light add up to white light. In art, they're like, colors that look good together, and in art, complementary colors are those that add up to black, but that's because art is talking about pigments. So please remember that when we're talking about light, complementary colors combine to create white light. Alright, where would we expect to find the image of an object formed by a concave mirror if the object was placed between the center of curvature and the focal point? And then it wants us to draw the ray diagram of that particular case. So I happen to know that the image is going to occur over here, which means it's going to be real. You can't see what I'm doing. So I'm going to put real space, and then we're going to draw the ray diagram to prove that. I don't have a ruler, so I'm going to use a random piece of paper. Remember that the rules for ray diagrams are pretty simple. You go parallel, then through F, and through F, and then parallel. So our intersection is like right here, which means our object is, here's our image. So that was the object, and then this is our image. So it did in fact occur in real space. Yay! Now, the next one's talking about something on the next page, which is kind of awkward. It's asking if the object is placed between the focal point and the vertex being the mirror. This case, where you're between the focal point and the mirror, is a makeup mirror. And that means that our image is going to occur in virtual space. Let's prove that. All right. So, parallel down through the focal point. This is the weird one. Line up with the focal point, but draw up towards the mirror. Then parallel. Your brain says, oh no, those don't intersect in real space, but I'm pretty sure that they should intersect somewhere. So I'm going to imagine a space behind the mirror where these lines look like they should intersect. And your image forms back here in virtual space. It's much larger. That's what makes this a good makeup mirror. You can see all your pores and stuff. Also, wow, look how crooked my arrow is. Got like the Leaning Tower of Pisa happening there. Oh well. All right. Describe the only image formed by a convex mirror. All right, well, concave mirrors we've just seen can form two images, and they can also form different sizes of images, but convex mirrors can only do one thing. They can create a virtual, upright, smaller image. They're used for like security purposes and for like your side view mirrors. All right. All right. When you're nearsighted, your eyeball is too long, which means that your focal length is too short, and you need a diverging lens to lengthen your focal length. A diverging lens is going to be a concave lens. To correct farsightedness, your eyeball is too short, which means your focal length is too long, which means you need a converging lens to shorten your focal length. And converging lenses are convex lenses. Remember that concave mirrors and lenses are backwards, so a diverging lens is concave, a diverging mirror is convex, and vice versa. Oh wow, that is literally the next thing I was supposed to write down. Converging lenses are concave. No. Yeah. Converging lenses are convex. Converging mirrors are concave. Yay! Alright, now thermodynamics. This is the stuff we just learned about, so you guys should be like super good at this. Heat transfer by blank occurs when electrons bump into atoms and other electrons. This is conduction. Direct contact between electrons. Heat transfer by blank occurs when large numbers of atoms move from place to place. This is convection, when you have atoms moving around in a fluid. Heat transfer by blank occurs when electromagnetic waves travel from place to place. Radiation. A cup of boiling water has a higher temperature than the ocean. True. The ocean is not boiling. A cup of boiling water has a greater internal energy than the ocean. This is false just because there's so much more water in the ocean. But again, that's not really something we discussed, and I promise that the test is on things that we discussed. Temperature is a measure of the average energy of a substance. What happens to the average kinetic energy of a substance if its temperature increases? The internal energy increases. That should make sense because temperature just has to do with how fast molecules are moving, and molecules are going to be moving faster if there is more energy. All right, now we're moving on to nuclear. What does the atomic number of an atom represent? Number of protons. What does the atomic mass represent? Number of protons plus neutrons. List the 3 major types of radiation and give their symbols. Alpha, which is represented with an alpha. Beta, which is represented with a beta. And gamma, which is represented with a gamma. Of the 3 types of radiation, which is the most penetrating and dangerous? That would be gamma, because it has the most energy and it's the hardest to stop. Einstein's famous equation E equals mc squared reveals that mass can be converted into large amounts of, well, we didn't learn about this, I'm going to write it down. Mass can be converted into energy, and energy can be converted into mass, but that's another one that we didn't really learn about. What type of nuclear reaction fuels the sun? That would be fusion, whereas we use in our nuclear power plants fission. All right, be able to solve the following nuclear equations. Okay, so this is beta decay. I can tell that because we've given off an electron. So when beta decay happens, the mass number stays the same, 214, and the atomic number goes up 1, so it will be 84. So then to figure out what atom you're dealing with, from the periodic table we learned that the atomic number 84 belongs to PO, or polonium. Now this next one, okay, this is kind of weird. We know it has to do with alpha decay because there's a helium involved, but this one's real funny. I don't like this. We didn't work any like this in class because here, basically this is going the opposite way. It's saying that you ended up with helium and iron, Fe, but you started with a neutron and something else. We haven't really worked one like that. You just have to make the numbers work out right, so it's not too difficult. If you look over here, we have a mass number of 54 and 4, so that's a total mass of 58. One of those masses is coming from the neutron, so our parent molecule must have had a mass of 57, because we have 58 over here, and now we have 58 over here. Our neutron does not have a proton, so our atomic numbers over here were 26 plus 2, which is 28. Since the neutron is not contributing any protons, then our parent must have had all of the protons, so it must have been 28. So again, we're going to flip back to our periodic table, and 28 is Ni, nickel. That one's kind of tricky. I don't like that one. This last one, this is more basic. It's also alpha decay. I can tell just by how much the mass number and atomic number have each gone down. So what we have to recognize is what alpha decay gives off. So we went from polonium to Pb, which is lead. Should have known that. Okay. So we went from polonium to lead. We went from 218 to 214, from 84 to 82. So it must have given off a helium nucleus that had 4 and 2. All right, well, that concludes this study guide. This is not comprehensive. That means that it's still totally possible to have questions from previous units that weren't on this review. So if you have time, I would recommend looking back through all of your previous reviews. But if you don't have time, this at least gives you a pretty good idea of the types of things you'll see. See you